Alright guys, so today we're going to do a redo of an old video from the channel, the most viewed video, and it's the Rank-Nullity theorem for linear transformations. So let's say we have a linear transformation T that goes from R3 into R4. Let's say that is given by T of XYZ. It's going to be the transformation that will take values, let's say x plus y plus z, 2x minus y plus z, and let's say we have, I don't know, x minus y, and just that, and let's say we have y plus z. So taking three variables and making it into a four-dimensional, or vector in 4 dimensions rather, not 4-dimensional, but a vector in 4 dimensions. Alright, so what we're going to do now is we're going to write the matrix of the linear transformation. So to do this, you're going to evaluate the vector 1, 0, 0, and that's going to give you your first column. So the first column is going to have 1, 0, 0, or the first position is going to be a 1. Then you're going to have a 1, 0, 0, so it's going to be 1 times 2, 2, minus 0 plus 0 is still 2. Now, the next one, you're going to have a 1 minus 0, and then here just 0. So that would be your first column. The second column will be when you evaluate 0, 1, 0. So you're going to have the y's are going to be the ones you pick up. And really the net effect is just picking the coefficients in front of the y. So 1, negative 1, negative 1, 1. 1, negative 1, negative 1, and 1. And then the next would be the z. So when you evaluate 0, 0, 1. And so the coefficients for the z are going to be 1, 1, 0, and 1. And once you have that matrix, you're going to do the reduced echelon form. In this particular case, I want to have 1, 0, 0, 0. And you would have to do Gaussian elimination. I chose my coefficients, so the reduced echelon form. Hopefully it's simple. And let me verify that what I said is correct. Indeed, that would be the reduced echelon form of that matrix. Alright, so with that, then you're gonna want to write the range and the null space of the matrix. Let's start with the range. The range is perhaps a little bit easier. What you're gonna do, you're going to locate your pivot positions. These are the leading ones in the non-zero rows. Those leading ones are going to correspond to the first and second column. As such, the range is just the span of the set that includes those two vectors. So 1, 2, 1, 0, and 1, negative 1, negative 1, 1. And that would be your range. Now for the null space, you will want to set your equations. In this case, you're going to have x plus 0 plus z. And you're going to set it equal to 0 because the null space is going to be the set of vectors for which the transformation becomes 0. So t of x such that t of x, or x is such that t of x is 0. So now the next equation is going to be y, because I'm in the second column, plus z equals 0. Now since z does not correspond to a pivot position, z will become a free variable, and I'm going to assign it a parameter t. Now putting this together, x would be negative z, which I'm going to write as negative t because z is t. Y is going to be also negative z when I subtract it, so it's going to be negative t, and z is going to be t. So any vector in the null space then is going to be of the form -1, -1, 1 times some coefficient or some constant t. So let me erase here and write the null space so I can then write the rank-nullity theorem or whatever it would add up to be. Alright, let me erase. I'll be right back. Alright, so what we obtain in our equations is that the null space is spanned by a vector of the form we said -1, -1, and 1. Now notice these two spaces live in different spaces. The null space lives in the domain or the domain of the function, while the range lives in the codomain. However, the relation between their dimensions is still it will hold true. That is, the dimension of the null space, which is called the nullity, is going to be equal to 1 plus the dimensions of the range. There's two vectors that span it. That's going to be equal to the dimensions of the domain, which is equal to 3. So indeed, that verifies that the rank-nullity theorem holds as we would expect on this linear transformation, because of course holds for any linear transformation, but when we're asked to verify that, that's what we're expected to do. So let me go ahead and erase, and I'm going to look at another type of transformation. And this transformation will be associated to the inverse of a matrix. So let me erase and I'll be right back. Alright, so now let's take a look at this type of problem where, let's say we don't have an explicit definition for the transformation, but let's say that t of 2, 1 is equal to E1. And let's say t of 1, 2 is equal to E2, where E1 corresponds to the vector 1, 0, and E2 to 0, 1. So let's try to figure out what would be the transformation t, or what it would look like. Let me erase this. Alright, so let's go ahead and take a look at how we would actually solve this. Well, firstly, one thing that we notice is that these two are linearly independent, 2, 1 and 1, 2. They're not multiples of each other, so in 2 dimensions that means they're linearly independent. So we can actually start computing. These are actually a basis of R2. So we can compute what the transformation would look like. Alright, so let's take a look at that. So we have that t evaluated at 2, 1 equals 1, 0. And we would like to know really what t of x comma y will be. And the same here, I also had t of 1, 2 equals 0, 1. And so I want to figure out what this is going to be equal to. So how do I do it? Well, let me draw you a picture. So let's say this is my R2, my domain, and I have R2, my codomain. What I know is that this vector, let's call this V1 and this V2. V1 is being sent, and I'm told that t is a linear transformation, by the way, that is important. Now, just thinking about, without doing the work, if we think what goes backwards, so if we think about t inverse, that's why I mentioned the fact that 2, 1 and 1, 2 are a basis, because otherwise this transformation would not be invertible, but it's going to be invertible. And the matrix transformation corresponding at t inverse is actually really easy to write down the matrix, because I know that t inverse of 1, 0 is going to be equal to 2, 1. Similarly, t inverse of 0, 1 is going to be 1, 2. So what that tells me is that the transformation, or the matrix for the transformation t inverse, is nothing but 2, 1, 1, 2, because remember the definition of the matrix associated to a linear transformation is just t of E1 goes at the first column, t of E2 goes for the second column. So that would be my transformation. Now you got to remember that the matrix associated to the inverse is the inverse associated to the matrix of t. So if I want to find the matrix associated to t, I only have to find the inverse of this matrix, and this is a 2 by 2 matrix, so I can do it with the shortcut formula. So I can do 1 over the determinant, which is 2 times 2, 4, minus 1 times, you swap the diagonal entries, well, nothing happens there, and you put negative in the off diagonals. So if you want to know what t inverse of x comma y will be, let's use that, or what t of x comma y will be, just use that formula that we just calculated, which is going to be 1/3 of the matrix 2, negative 1, negative 1, 2 times x comma y. So that would give us then 1/3 of 2x minus y and 2y minus x. When you multiply, you get negative x plus 2y. And that gives you what the transformation would be. I was going to solve it in a different way, the way I did it in the original video, but I think this is much easier. Yes, I'll leave it at that then. So I guess 9 years later, I prefer this way of solving it than the one I had. I'm going to drop the other video in the description just in case you want to check it out. Just make sure you increase the quality to the maximum because it's extremely blurry. But thank you for watching, and if you want me to solve any different kind of problem or something, just drop it down in the comment and I'll be on it. So thank you for watching, and I'll see you in the next one.